So the speaker for today at this session is Dario Beraldo from University College London. And he's going to speak on the Ramanujan conjecture in geometric Langlands.
Great, thanks very much. It's a great honor to speak at this conference. Yeah, so here's the title, and I'm gonna use slides, and I'm gonna write on them at some point of this work. And for example, here is what I wrote down is the preprint and the archive preprint on which this talk is based on. So let me start with the original Ramanujan conjecture. I remind that, and that would be a source of inspiration for what I wanted to explain in geometric Langlands. So the Ramanujan conjecture starts with this beautiful modular form delta, which can be defined as an infinite product, like so. And then, so you can expand this infinite product and make a Taylor series. And of course, this Taylor series will start with the power 1 of cube. So there's this zero constant term. And once you make this change of variables, this becomes a modular form of weight 12, and it's cuspidal. Cuspidal in this case means what I just said, that it has zero constant term. And so Ramanujan conjecture that, so this sequence, the tau sequence, is called Ramanujan tau sequence. And Ramanujan predicted a bound for these tau numbers. And so that's the bound I wrote here for the primes. Well, actually, Ramanujan conjecture consists of 3 parts. The first 2 parts are about multiplicative properties of the tau numbers, and then the third and most deepest part of the conjecture is this bound. In fact, very deep bound, and it was proved some 50+ years later as a consequence of the Veil conjectures, which were proved by Delin. So in particular, the Riemann hypothesis part of the Veil conjectures. And so these advanced techniques will not matter for us in this talk. What matters is an interpretation of this bound, of this story provided by Satake in the 60s, which interprets this bound as a temporary condition. So more precisely, so if you start with delta, which is a cuspidal modular form, from that you can construct a cuspidal automorphic representation. And this cuspidal automorphic representation decomposes into local factors. It's a product of local factors, and this bound precisely says that each of these local factors is tempered. So that's maybe a reinterpretation, and I want to keep this reinterpretation. I want to keep a very much an open mind on this interpretation, on this Ramanujan conjecture. Namely, I just want to view it as a template or as a skeleton for other conjectures that can be made more concrete. And so the skeleton for me, the naive point of view, is that whenever you have a cuspidal thing, and I don't specify what thing it is, then I'm asking whether it is also tempered. So this the implication cuspidal tempered. That's for me the skeleton of the Ramanujan conjecture, and it can be manifested in many ways. But of course, this implication is absurdly general, and it cannot be true like that in all contexts. In fact, there are some contexts where it's already known to be false. So you need to, but when it's false, maybe it's not too far from reality. So you need to add more conditions to cuspidal. But anyway, that's the general philosophy, which needs to be adjusted. So next page, that's what I just, the first sentence is what I just said, that this implication is absurdly general. So it's false many times. And maybe the theorem that I'm going to present, the view of this comes as a surprise in that you don't need any adjustment at all. In geometric Langlands, the word cuspidal and the word tempered make sense, and you do have an inclusion. So it's a fully faithful embedding of categories, but it's just about objects. So it just says that any cuspidal objects in the category of the modules on Bungie is actually tempered. And So the statement is compact. It's compact, but maybe the caveat, the warning is that lies in the definition of temperedness in geometric Langlands. Namely, usually tempered things are analytic things, and I will considering only the algebra geometric aspects of the conjecture. So I don't have, for example, L2. I don't have decay at infinity in the way we think about it. So those are usually the words that appear in tempered, like L2 plus epsilon. The definition of temperedness will be different. And one, for example, the main obstacle is that what I wrote here is that it's not clear that it depends on the growth of the sheaf near infinity. So maybe reaching ahead, I'm going to say that the stack of G bundles that we have been considering is not quasi-compact, so it makes sense to look at its tail near infinity. And it's not clear that so if I give you a sheaf, it's not clear that the tempered condition depends only at the end near infinity. It's not clear from the definition, but it will be clear from a variation of this theorem that I will explain later. Right, so here's the plan for the talk. So far was the introduction and the statement of the main theorem. So now for the big part of the talk, I just want to play with the geometric Langlands conjecture. So this is a conjecture. Nevertheless, I'll use it to deduce that the theorem that I stated before is forced on us by geometric Langlands. So that no correction is needed. I'll explain that it follows from geometric Langlands. So far, in this point, I'm not doing anything. I'm just playing with the conjectures. Yeah. But so one thing to notice, one thing to be remarked is that, so coming back to this theorem, I don't have a direct proof of this theorem. So the proof will go as a different route. We will play with geometric Langlands and we'll find a stronger conjecture. So the stronger conjecture looks for an intermediate category that ought to lie between cuspidal and tempered, and then so with this intermediate category, we divided the problem into two parts, and this left part will happen to be known. So this part will be okay, and then the to-do part will be this one. And this is the third part of my talk, where it'll be clear by then what this C is with this intermediate category is, and we should prove this inclusion. Okay, so that's the plan. Any questions on the introduction or on the logic of the talk? Okay, so let me start with it. I change page, but it doesn't seem to change page. Okay, now it changed page. So by being in this conference, I learned that geometric Langlands means many things. I will concentrate on the algebra geometric aspects, and in particular on the geometric conjecture put forward by Arinkin and Gatesbury. And
there was a quick question in the chat from Aswin about if there's also a local and a global version of the conjecture.
Sorry, why don't I see the chat? Anyway, so this is the global version of the conjecture, as far as I understand. So this is the global version. Cuspidal demodulus on Bungie should be tempered, and there is also a local version, but I didn't think about it. But the words make sense, although the temper would be different, and yes, but so I don't really know the status of that one. Okay, now I can. Okay, so like, is that okay? Okay, thanks. And then I should say the tempered, yes. So it's a global thing, but it can be, it's defined locally. We'll see. In a way, we'll see later, much later, when I actually define what tempered is. We'll see that it has a local flavor as well. So I'm on this page on the geometric Langlands conjecture, and so it's an equivalence of categories. On the left-hand side, we have the automorphic side, but I can see I'm not writing anymore. So this left side is called automorphic side, and the right-hand side is called spectral side. And I should probably explain the spectral side because it didn't appear, for example, in Jörg's lectures, while the automorphic side appeared. Yes, this is one of the main innovations put forward by Arrington gate theory. So it's a general feature. So this I'm talking about incoherent sheaves with nilpotent singular support on the stack of local systems for the Langlands group. And so most of it is general. We need to have some scheme or a stack which is quasi-smooth, which is the best next thing after smooth. So it's only mildly singular. And in that situation, we have a singular support map that associates to coherent sheaves or incoherent sheaves, associates its singular support, which is a conical subset of this H-1 of the cotangent bundle. So I will draw a picture later, but this H-1 of the cotangent bundle is a space living over Y, and it has fibers are vector spaces, and singular support lives there. Conical subsets are conical with respect to this vector space structure. And of course, this is a refinement of support. So if I just remove singular and I consider support, well, what would be the answer to what's the support of a coherent sheaf? It's not. It will be a subset of just of Y, right? So that would be support, and singular support is a refinement of that, right? Which is possible when we are in the positive mood situation. And so the analogy here is maybe instead of calling singular support, we can call it wavefront. In distribution theory, distributions have a wavefront, and the delta distribution, for example, the wavefront is the entire cotangent fiber. Okay, but we don't really need to know the details of the construction. What we need to know is that in our case, where Y is log-sys G-check, which is quasi-smooth, so it's good. This H-1 of the cotangent complex is concrete. It's a set of pairs where sigma is a local system, and A is a horizontal section of this flat vector bundle associated to the local system and the Lie algebra of the group. Okay, and so this is a concrete form of what this space is. Of course, like I said, if fibers over log-sys, just by projecting onto the first coordinate, and the fibers are vector spaces. But inside it, we can consider the global nilpotent cone, which is different from the global nilpotent cone for X bundles. It's this nilpotent cone that only this nilpotent cone I will consider in this talk. And so the requirement is that so on these pairs, you will want this global section to be nilpotent, which means just nilpotent as it's enough to say it's nilpotent at a single point of the curve. X is my curve. And if it's nilpotent at single point, it must be nilpotent at both points. So that's the set I'm going to consider inside this shifted cotangent bundle. And then once we have that, we can define the spectral side of the geometric Langlands conjecture as those incoherent sheaves with singular support contained in the nilpotent cone. And if we do something different, instead of considering the nilpotent cone, we can consider the zero section. So this zero is the zero section of this map. So consider the locus where this section is zero. Then we recover quasi-coherent sheaves. So quasi-coherent sheaves sits inside this Langlands category. Okay, so I have a clean page for some pictures because this is probably the most obscure thing in this talk. So consider a general situation. We have our space Y, and so we form the H-1 of the cotangent of Y. So for example, if I have a little point here, little y, so what's the fiber of this space would be H-1 of the cotangent space. So the cotangent complex of my scheme at a little point. And so that measures the singularity. So the bigger this vector space is, the more singular the point is. So other points will have vector space of lower dimension, and some smooth points will have no vector space coming off them. Okay, so this geometric picture is the geometric shadow of the category, and so we can play the game that we were playing in previous page, where we inside this space we can consider nice subsets, and we restrict the singular support of the objects we want, and we obtain nice categories. So this last sentence that I was saying here is that if you change color, if you look at only at the Z, if you look at the zero section, so you restrict support onto the zero section, you get QCO of Y. Okay, so InCo lives over the entire picture, QCO lives over the zero section. Then if you do the complement of the zero section, so this purple complement, so you get the quotient, which is the category of singularity, so-called. So it's the incompletion of dBco of Y divided by pair for Y. So this category of singularity is appearing in the theorem of factorization, for example. But you can do something different. For example, change color, take blue. What if I take a single fiber? So I restrict the singular support of objects to be in that fiber over my point. And then I get the blue category, which is incoherent sheaves on the formal completion of your scheme at the point. And you can do something even more different. Think maybe. Just what if I take just the category, just restrict singular support to lie at Y, and then I get QCO of Y of the formal completion. And so what I'm saying in the particular case of local systems is that, for example, the trivial local system, the fiber will be the entirely algebra. Okay, and then you can restrict the singular support to be on the nilpotent cone in the algebra. And that gives rise to this category that appears in the geometric Langlands conjecture.
Dario, the last thing you wrote didn't show up on the screen. Also, there's a question.
So let me read the question. No, so it's not related. Yeah, as far as I know, it's not related. So Eclipse on not mirroring. Okay, so now you can see, so what I was saying is that in the particular case of local systems, you can look at the trivial local system. And if you run the definition, what you get, what's the fiber over the trivial local system is the entirely algebra. And so similarly to other spaces would be something related. And inside this Lie algebra, you single out the nilpotent cone and you restrict singular support to live in this nilpotent cone. So an example is for my curve to be P1. In that case, everything is explicit. So local system for P1 is naively is just a point, because naively you only have the trivial local system, but less naively it's an odd vector space, which is shifted dual of the Lie algebra, shifted Lie algebra really. So either you write it as an spec on exterior algebra, or to better keep track of the degrees, it's this odd, it's symmetric algebra over this odd vector space divided by G check. And so you don't need to know any derived algebraic geometry to say that what quasi-coherent sheaves on it are. It's just modules, well, differential graded modules for this differential graded algebra, this exterior algebra, G invariant. Actually, this should be G check. Okay, so this is quasi-coherent sheaf. And then there is Koszul duality. So we want to enlarge it. To enlarge it, you use Koszul duality. So it's Koszul duality between exterior and symmetric algebras. And so the bigger thing is modules for this symmetric algebra, shifting degree 2. Okay, so and that's actually invariant sheaves. And now we will look at something with nilpotency or support. And the way to do it is this. So let's understand this category geometrically. So without the -2, there will be quasi-coherent sheaves on a vector space, which is the dual Lie algebra, right? Well, and divided by G check, because everything is G check invariant. And usually I denote by double arrow the fact that I'm shifted the degree of the variable by 2. Okay, so that's very geometric. It's quasi-coherent sheaves in a vector space, essentially. And here, running the definition, this is the same, but when we restrict the support to be near 0. So those are the quasi-coherent sheaves on the same vector space with support, with set theoretic support at 0. And of course, there is something in the middle, which is quasi-coherent sheaves on the same vector space, shifted again with set theoretic support in the nilpotent cone. And so that's exactly what in conilp is in this particular case. Okay. And so this discussion gives the definition of tempered. I mean, it's not a definition because it depends on the conjecture. But if you believe in this conjecture, if you buy this conjecture, then of course we have the inclusion here of quasi-coherent sheaves on conilp. That's just the 0 section, and that by default should correspond, by definition, should correspond to tempered D modules. Okay. Except, of course, this is not well defined because it depends on the conjecture. But let's use it nevertheless. And later I'll give the definition, the proper definition. Okay. Any questions so far? Okay, so this was tempered objects. Let's now review caspital objects. And that's much less obscure because it's similar to the classical Langlands theory. Okay, so we take a parabolic subgroup P, and the quotient is Levy, and so we have this correspondence between groups, an inclusion and a projection, and accordingly we have we have a correspondence between bundles. I see. I'm not writing. Okay, so you have band P. That there is an induction to band G and an induction to band M. And traditionally, these maps are called P and Q, a little p, maybe. And so the Eisenstein is just the pull-push in one direction, and the constant term, which is the right adjoint, is the pull-push in the other direction. So the Eisenstein will be Q upper star P lower shriek, and the constant term is P upper shriek Q lower star. Yeah, so for those of you not familiar with D modules, I'm just going to use, I'm not use much about D modules. I'm just going to use that they have 6 operations. So those are examples of 6 operations, pull-push. Okay, and so we have these adjunctions for any parabolic, and the cuspidal objects are the ones, are those objects filled by all constant terms. So if cuspidal means that if I'm here and I apply the constant term, I get 0, not just for P, but for all parabolics, excluding G, of course. What happens if P is G, then this adjunction is the identity. So I exclude that. And then, okay, so this is a paradigm for Eisenstein series and constant term, which is the right adjoint. And the same paradigm happens on the spectral side, where you have the same diagram. And the same functors pull-push. Here you need to be careful. You need to prove that this nilpotent singular support condition is preserved by this pull-push, and it's proven by Avinti and Gateway in this paper where they introduced these categories. So that's all well defined, and of course it makes total sense by symmetry to define cuspidal spectral Langlands objects like so as the kernel of this constant term, and then geometric Langlands is this equivalence of categories between this category here and this category here, but it's expected to be compatible with natural operations that you can perform on both sides. And one of these natural operations is this one. So it's expected that under Langlands for G and Langlands for M, these pairs of functors, these 2 pairs of functors should correspond. Okay, and so it makes sense to ask what are the cuspidal objects on the spectral side, and whatever they are, well, that's the definition, and whatever they are, this subcategory should correspond to this subcategory if you believe in Langlands together with its compatibilities. But of course, cuspidal objects on this side are very important and very interesting. Cuspidal objects on this side, they don't appear in the literature. That's because it's easy to say what they are and they have a different name. So let's go to the next page and see. So there's a lemma coming from just the geometry of local systems that says that cuspidal local systems, cuspidal coherent shapes on local systems are the same as incoherent shapes on an open substack, which is the substack of irreducible local systems. So irreducible local systems are those local systems. So, so for example, for GLN, local system is a G bundle with a vector bundle with a flat connection, and being irreducible means that there is no proper subbundle preserved by the flat connection. So that's what irreducible means for GLN. And so that's what we get by an easy calculation. And then the observation, the key observation that leads to the Ramanujan conjecture is that the nilpotent cone that I'm considering and this locus of irreducible local system don't go very well together. Because so what does it mean to be what's an element of nil? That's a local system and an horizontal section of the Lie algebra bundle. But this horizontal section of the Lie algebra bundle immediately it gives a reduction to a parabolic. So immediately it gives a vector bundle, a subvector bundle preserved by the connection. So that means that this global section must be 0. In other words, sorry, it's right. So this is pairs sigma and A, where A is a horizontal connection of this Lie algebra bundle. But if A is non-zero, then that exhibits sigma as reducible. And so since we are in the reducible locus, that's impossible. So A must be zero. And therefore, there is no difference on the open part of the reducible local system. There is no difference between incoherent sheaf with nilpotent singular support and quasi-coherent sheaves, right? So that's telling me that the cuspidal objects on the spectral side are contained in QCO. So if you go back to my chain of Langlands duality here I have an inclusion. I can have a third part. Which is the irreducible locus, okay? And that's included inside here. And that should match conjecturally with the cuspidal part. Since you have an inclusion here, then you should have, if you believe in geometric Langlands, inclusion here. And that's exactly the conjecture as it was stated. Okay.
Could you just repeat the definition of the cuspidal D modules?
Yes. So for any parabolic, okay. You have this adjunction, and you require that the constant term are killed. So if you go back to Ramanujan original conjecture, so this delta was cuspidal, meaning the constant term, literally the constant term of the Taylor series was zero. And so here is which is parallel. But the original Ramanujan conjecture was for the group GL2. For the group GL2, you only have one parabolic, so you expect only one condition, and that was the condition, the zero term. And when you go for other groups, you have more parabolics, so more conditions. Okay, so yeah, so we got to the conjecture. Also, I try to convince you that if you believe in geometric Langlands together with its compatibilities, then you should believe in this conjecture. And now let's try to prove it. Well, that's not the time yet, because like I said, I don't know how to prove it directly. And so my strategy is to find an intermediate category between those two that makes the problem a two-step problem, and each of the steps should be easier. And to do that, we need to do something funny with Eisenstein and constant terms. And we want to combine them into a single functor. And so there is only one way to do it, but it's a bit technical. So this page is full of lies. These warnings, I explain them. But let's go with it. So how do we form a single functor using this? Well, first of all, to go back to the page, I can go this. I start from band G, I apply constant term, and I come back. That's an end functor of band G. And then I want to do it for all parabolics, and then combine in a unique way. I mean, there is only one way to combine them. It's about, well, I'll say that in a second. But so we just combine them, and this is schematically written as an alternating sum, but it doesn't make any sense to alternate sum. It doesn't make sense to do -1 with sheaves. So this is kind of the analog in number theory or in classical representation theory of the linguistic duality functor. So I wrote it this schematically. It doesn't mean anything. Rather than that, it's not a direct sum. It's not an alternating direct sum. It's a co-limit, because parabolics assemble according to the Dinkin diagram, according to the subset of the Dinkin diagram, and the subset of the Dinkin diagram form a poset, and I use that poset to construct this functor really. For example, for GL2, so for GL2, I only have, so see, I fix a Borel, and so I only have two parabolics between the Borel and G, namely the Borel itself and G itself, and I'm using G as well. So I have Eisenstein constant term, apply one after the other. And since that's an adjunction, this is the co-unit of the adjunction that maps to the identity. And the identity turns out to be simply Eisenstein G composed with constant term G. So I have a uniform way to write it. And for more difficult groups, I have a sequence of cones co-limited in the direct sum. So that's the functor. But that's still a lie because I'm not really using this Eisenstein constant term exactly as I defined them before. I need to modify them to make them equivariant for equioperators for G. And this is a technical point which is irrelevant for today, but nevertheless, let me say. So let me say one thing, reaching ahead. So here I have equioperators for G acting. Here, so if you wish, here I have equi for G acting. Here I don't have equi for G, I have equi for M. So it doesn't make sense to ask for equi for G acting on both sides at this moment. So, but there is a canonical way to modify them to enrich it so that it gets an action of equi for G. And so there is accordingly a canonical way to modify these functors. And those are the functors I use. So technical remark that is irrelevant. Nevertheless, with any definition, even with this fake definition, we see that this Linguistic functor, which is combination of constant terms, is tautologically an identity, the identity on the Caspidal part, just because all these constant terms except for one will kill the object. So you remain with the identity. Right. So let's describe how this linguistic functor looks like and why it's useful for us. And so it's useful because it can explain this. It messes things up at infinity. So like I said before, Bungee is now quasi-compact. So you can look at near infinity, or rather I can look away from infinity. I just look at quasi-compact open substacks and extend, and take sheaves on this quasi-compact open substacks and extend. Right. So the open, we don't need to know how these open substacks are defined, but one way to define is using the Hardy-Narasimhan theory. So you can bound the Hardy-Narasimhan weight of a bundle. If you collect all these bundles with the same Hardy-Narasimhan weight less than something, you get an open substack, and then as you relax this bound, you cover all Bungee. Okay, and so this the linguistic functor on the spectral side. It does this. It changes Schrick with star. So just a question, can people hear me?
Yeah, we hear you. The AV team commented that you might want to mute your video if you're having network issues.
My only network issue is to connect the iPad with the computer, and it's happening on AirPlay, and I think that's the problem. But I can mute my video.
We can hear you fine. I can hear you.
Okay. So this problem keeps, I don't know, it keeps on disconnecting. So the sharing just keeps. Okay. Okay. So so there's a theorem of Lin-Chen going after conjectures and work of the Ringfeld-Wang for SL2 and Gaitsker in general for general G, that explains what the linguistic functor is. So it was defined as a crazy combination of constant term and Eisenstein series, but from the point of view of non-quasi-compactness, it just take a Schrick extensions and it moves it to a star extension. So we should, so it's not exactly that it takes a Schrick extension of a sheaf and it moves it to a star extension of the same sheaf. It's a different sheaf. F prime U is different from F U, but the map, the functor from F F(u) to F(u) prime is an automorphism. So we can actually just ignore it, can pretend it's the identity. So it's an automorphism of quasi-compact things, and it changes the way you extend to infinity. And so from this information, it might be that the linguistic functor is an equivalence. For example, it's very close to being an equivalence, but actually spoiling it's better. It's not an equivalence. It's more interesting than an equivalence. So let me show you how close it is to being an equivalence. For example, let me show it's fully faithful on these Schlick extensions. It's really easy. So suppose I have two Schlick extensions. Okay, same problem again. So since J lower Schlick is fully faithful, I can remove it. But then since the prime thing is an equivalence, I can insert it. So this is Holmes in D modules on U. And then this was in the first one was D modulo on G, and then J lower star is fully faithful. So D modulo on Banji, J lower star. Okay, so I show that the linguistic this functor is fully faithful on pairs of objects that are Schlick extensions. And yeah, so actually any object whatsoever can be written as a combination of Schlick extensions. So this is very close to being fully faithful, but we'll see that it is not. And to see it's not clearly, let's perform the same construction on the spectral side. Okay, so on the spectral side, we can do formally the exact same thing. I have constant term adjacent series. I combine them. I do this alternating sum, which is not an alternating sum, it's a co-limit. And I have a functor from inconil to inconil. And this functor is very far from being an equivalence if you look at it. So this is a theorem of mine from 2019, description of this functor. So first of all, it's of interest for us, you see it here, because the first step of this functor is just to kill everything with singular support away from the zero section. It just projects down to the spectral analog of the temper part. So it just kills everything non-tempered. And then it does some more killing. Namely, it just tensor with an object, which I call the Steinberg object, which is a direct analog of Steinberg object in representation theory. But in this context, it can be interpreted as lying a little bit as the structure shift on the locus of semi-simple locus. And the reason I say that is because if I look at the fibers of the Steinberg object at a local system, so it's always either 0 or one-dimensional, say C. So it's 0 if sigma is not semi-simple, and it's one-dimensional if sigma is semi-simple. But it's not always, it's shifted by some shift, some homological shift that depends on sigma. So it's not really a structure shift. And there is no control of the shift, they jump. I mean, there's an interpretation of the shift, but it's not, they vary wildly across this local system. But nevertheless, so this functor looks very different from the other functor because it's a composition of two things, each of which kills objects. Okay, and so comparing this description on the spectral side with the previous description given by Lin-Chen on the automorphic side is actually a statement generating machine because those two functors should match under geometric Langlands and therefore their properties should match. And so let me give you 3 examples. of this game. So we said that this is almost an equivalence. I argue that. On the other hand, this one is not at all almost an equivalence. That means, for example, this one kills object. That means that this one on the automorphic side must kill object. And once we know that, we can look for one, and then so it just kills the object, the main object that you can write, which is not an extension from something finite, which is the constant sheaf of Bungie. Of course, it's not an extension, a sheaf extension, and that actually gets killed. So we will not need that, but I thought it was fun to mention. Now we can go in the other direction. So we still think that this linguistic functor is almost an equivalence in view of this virtue of this computation. It means that on extensions from something finite, it is fully faithful. And so this functor also must be the same. So in fact, it's a theorem that we'll not use. Theorem, again, in the same paper that I discussed, which is that saying that the linguistic functor restricted to co-nil. So the finite object of local system G is fully faithful. So not only if I start with a co, so in co is like, in co stands to finding to vector spaces, like co stands to fine dimensional vector spaces. So if you start with finite objects, then they survive both of these potentially killing operations. Not only do they survive, but also they don't lose any information. So this category of co, a finite object, gets moved isomorphically by those two things. But it gets compressed inside QCO, you see? So that brings me to the third application of this parallel between those two descriptions of the linguistic, which is, okay, let's look at their essential images. Okay. I want to look at their essential images, and they should match under geometric language. So let's look at the automorphic side. What's the essential image? Well, there's some words to be said, but the essential image is just star extensions and objects generated by those under calling. That's what it is. So if, of course, you see, the essential images contain star extensions, but also contain things formed out of them using colimit, and that's what I denote by this triangle parenthesis. And that's, I give a name to this category, is the categories generated by star extension. So the star generated category. And as we noticed before, the star generated category contains the cuspidal category, because surely the linguistic functor was the identity on cuspidal objects. So that's what we have on the automorphic side. On the spectral side, if we buy this fact that the Steinberg object is the structure shift on the locus of simple local systems, then you see that the image is the category quasi-coherent shifts on the locus of simple local systems. And that's a slight lie, because this locus is only constructible inside Loxis. It's not locally closed, so it's not defined. It's not defined as a substack. Nevertheless, this category is possible to define. So the category exists without the stack existing. This is a difficulty that doesn't matter for us. So let's pretend everything is okay. And so the spectral side, we have a double inclusion, and that's clear from the definitions. So here the image of the linguistic functor is here, and like between the cuspidal spectral objects and the temper spectral objects. So that's my intermediate category on the spectral side, and should correspond to the intermediate category on the automorphic side. Namely, the next page, I have, so geometric Langlands should go this way, and those are three flavors of geometric Langlands. The cuspidal flavor, this middle flavor that I discussed, this temper flavor, and here I didn't write it, but it's the full flavor with all D modules and all inference shifts with the potential. So that's a picture. And that brings us to the conjecture, right? Because now the Ramanujan conjecture has been split into two parts, and the left part, luckily, is okay. It was known before. It's due to the influence gate theory. Explained that classical objects are obtained by star extension under co-limits. It also follows from Langlands theorem, but it was known before as a theorem of the influence gate theory. So it remains to prove the latter part. Okay, and so this is the refined theorem that I was mentioning at the beginning. Okay, and it explains why the tempered condition depends only at infinity, because so if I have a sheaf on Bungie, what does it mean to look at infinity? It means that, well, I take a large quasi-compact open, and so I have a map like that, a junction map, and then the kernel of this map is the part of F that I can see near infinity. So J is this inclusion of this open part, and I is the inclusion of the complement. And since this is tempered by this theorem, this is star generated, so it's tempered. So deciding whether this is tempered is equivalent to deciding whether this is tempered for no matter how big the open that I excluded. So in this sense, after this theorem, the definition of tempered object depends only at the end near infinity. But now we need to get back to work, because I didn't give you the definition of tempered that is independent of the conjecture. So no theorem can be proven without that definition. So let's give it now. And it hinges on this derived stack equivalence. And here I have a question for physicists, because I don't know the terminology. But anyway, so let's discuss the Ecke action briefly. So first of all, I can consider this. I pick an element, a point of a curve, and I look at this double quotient. It's the double quotient of the loop group at that point divided by the arc groups left and right, and I look at D modules. And this, by the usual Ecke paradigm, acts on the category D modules on Bungie, it acts by Ecke modification. And I guess those could be called derived operators. With a question for physicists. The difference with the usual situation is I consider D module, all the derived category of D modules versus just pervert sheaves. So usually people consider pervert sheaves on this quotient, but here I consider the entire derived category of D modules, and that's why it's called derived attacker. Derived attacker is the theorem that describes this Langlands duality for this category. And here it is, due to Beraldo and Finkelberg. And you recognize here our old friend, Indranil, for Loxis. Jacques on P1. I gave an example before. This is the Langlands category in genus 0 and appears there as the spectral side of the derived stack equivalence. And so how is this related to the usual geometric stack equivalence? It's because one realizes that this category has a T structure. The derived category of D modules has a T structure. And let's take the heart of the T structure. And the heart of the structure of D modules is the abelian category of pervert sheaves. So on here, if you take heart, you get pervert sheaves. Giovo equivalent pervert sheaf on the fine Ramanujan. And here, if you take arts, everything goes away. So nilp goes away, this shift goes away, this G goes away. You get a representation of G check, abelian category representation of the underlying group. And so that, as far as I know, is the usual physics. Well, the usual geometric stack, which is the usual duality between Tooth operators and Wilson operators. But here I need a derived enhancement, which is this. And now I'm ready for the main definition of tempered in geometric Langlands. That's so using these two ingredients. So it says that an object is tempered if the part of this category that lives over the punctual nilpotent cone, so nilpotent cone minus 0, that is act trivially. So what is this category here? Well, it's what I was doing in the picture before, right? It's the category of singularities of Fluxes for P1. So it's Q nil divided by Q code. So in the picture, what is the category away from the zero section? Okay. So this is the picture of the singular support, and I'm looking at just the category away from the zero section. Okay, so you see that this definition is a little bit difficult to work with because. So what do I need to do? I'm considering this object. Now I'm considering this category. I need to move. So this is a subcategory here. I need to move it via the derived stack equivalence. I get a subcategory here, and then I take this subcategory and I let it act by echo operators on my object, and I should get 0 for any time I do that. So since this passage, this theorem is a deep theorem, this definition is obscure. So once and for all, we can clean it. And here's my suggestion for how to clean it. So here we did take hearts to recover from this theorem, the usual geometric static theorem. Let's do something completely different. Let's not take hearts. Let's look at something. Let's look at the part of the category that lies homologically at minus infinity. So I have T structures. So anytime I have T structure in general, so I have a category with a T structure, I can look at objects that live at minus infinity in the T structure. So like so. And here I just recall the Ratsutake. And a fact is that like I said, this is a T structure, and let's look at what happens at near minus infinity. And surprise, we get exactly on the spectral side, this category, the part of the category lives over the punctual nilpotent cone. So this was the category that appeared in the definition of tempered. So it turns out that under the derived stack, this is moved to the subcategory of infinitely connective objects. And so I can form a corollary, which might be a definition after all. I mean, we can, in future talks, maybe we could take that to the definition. But it was motivated by geometric Langlands and derived stack. It says that F is tempered if and only if this part at minus infinity of the spherical category acts by 0 on it. So you see, this corollary, or if you wish, this definition does not involve derived stack, does not involve geometric Langlands. The G dual doesn't appear, so this is more concrete to work with. And this is the formulation I will use in the next 0 minute. So let me have 2 more slides. So what I should compute, in view of what I said, is that if you take an element of the spherical category lying at minus infinity, I act in the echo way on a star extension, I should get 0. And a quick trick, so there's a lot of things to check. A quick trick reduces it to one thing to check, which is for the push forward along the diagonal of the dualizing sheaf or the constant sheaf. So I just need to check that for any element at minus infinity, if I echo act on the left on this push forward diagonal, I get 0. So one statement only. So now this echo action I can rewrite explicitly, and here it is. It's like that. It's a pull push. So my S is an element here. Is an element in D modules here. and then I pull it along here, and I push it along there, and I should get 0. So what is this? So this is the global Eckert stack. So it's a pair of two G bundles on the curve that are identified on the puncture curve. And so this map just forgets the identification, just to remember the two bundles. And this map R stands for restriction. I just restrict at, not just restrict the curve to a disk around little x and obtain this double quotient. This double quotient parameterizes two G bundles on the disk at x that are identified away from the origin. Okay, and so I had just this computation. If I start with something at -infinity here, where should I get to 0? And so I divide this problem in 3 parts. The first part is the fact that the pullback here preserves things that are -infinity. So if I start with -infinity, I remain near -infinity. And the second part is easier. This push forward preserves -infinitely connective objects, but it just does more. It just doesn't move you to the right of where you are. So if you are at -infinity, you remain at -infinity. If you are at 0, you remain below 0. And then the third part is, okay, so if you believe the part 1 and part 2, you get a shift on a D modulo on the product, which is at -infinity. But in this case, there is nothing at -infinity, only the 0 shift. And that's what that concludes the proof. And just remark that this first step is where the geometry lies. And then this is easy, follows from the affineness of indefiniteness of this map H. This is easy, well known. This is where the meat is. But I'm out of time, so I'll stop here for questions. Thank you very much.
Yeah, let's thank the speaker.
Thank you.
Any questions? Have some questions, but see if anybody else has some first.
Jörg has a question. Aswin
Okay.
has a question.
Please just ask. I don't see. Oh, I should.
No, okay, yeah, I had a difficulty unmuting myself. Hi.
Hello.
Yeah, thanks for the nice talk. So I have a terribly naive question about sort of the origin of the name tempered in this context. I mean, what I would sort of trying to compare this to these variants of geometric Langlands I'm a little more familiar with. I mean, there one can see a certain parallel to the classical theory of automorphic forms, where one has a Laplacian on, say, some quotient of the upper half plane, and then, say, temperedness is about, say, growth at infinity. Now, in the context, say, of the geometric Langlands, as now, for example, being developed in an analytic version by Ittinghoff, Frankel, and Kashdan, well, I guess the first question is sort of what would be analogs of these cusps or points at infinity, and these should be the singularities of the Hitchin Hamiltonians, taking into account that the Hitchin Hamiltonians basically replace the Laplacian in that case, or take the role of the Laplacian in this case. So one asks sort of what are the singularities of these differential operators, and those are found at the, say, wobbly bundles using this Donagi-Pantev terminology. So I was wondering if there's any chance or hope or hint concerning a possible connection between, say, growth properties near singularities of, say, Hitchin Hamiltonians and temperedness in the sense that you're using, or whether this is, motivated by, different structural properties, to use the word tempered in this context.
This didn't look like a naive question at all. I guess I should, maybe, I should, after you give I should learn from your talk.
Okay, next. Yeah, maybe it's something for discussion rather than, maybe it's not something one can expect a quick question to, but anyway, I wanted to formulate it.
Yeah, that's great, because for a while I was trying to formulate the temper condition as a decay at infinity, but I only see this kind of this cohomological phenomenon. For example, I see the T structures at minus, so weird things. Who considers T structures at minus infinity? And yet there are some nice objects there. And so all cohomological things that could, with a lot of imagination, become things at infinity, but no passage to actually real things was able to do. So, but I'm not expert in this analytic thing. This is new analytic thing by, I think, of Kashtan. So maybe that's a good direction to go.
Maybe it's
there's also work with,
yeah.
Yeah, there's also work of Kashtan on a more refined Ramanujan conjecture, but ongoing. I can refer you to a talk by Kashtan.
Okay. Well, just
So,
okay.
sorry.
I mean, there's a kind of observation. It seemed from looking at their papers that they're using quite a lot of, say, input from geometric Langlands, say, as has been developed in this algebra geometric community. And well, maybe ultimately, I mean, this would be my hope. I'm coming from the other side, right? So my hope would be that ultimately there's a rich interplay between sort of these algebra geometric and categorical aspects with analytic aspects, where also maybe somehow what happens in theory of automorphic forms could well serve as a inspiration or so, in the sense that, for example, what one could expect is that somehow these deeper algebraic aspects are somewhat deeply hidden in like singularities of the eigenfunctions that Kashtan et al. Or well, Eating of Frankel Kashtan are studying. Anyway, just a wild speculation that I felt sort of thinking about these matters in the preparation of the talk, and hearing your talk well, was suggesting itself.
Thanks a lot.
Aswin, did you have a question?
Yes, I do. My question is, Lustig, in a lot of his works, especially extending the Springer theory and so on, in the local context, defines something called a cuspidal local system. Is there any sort of compatibility with that sort of notion and the notion of cuspidal appearing in this global geometric Langlands story?
Probably the formulation of the definitions is similar, but the geometry is misleading in a lot of ways. I mean, I spend a lot of time looking at old papers or classical papers and try to move them, and this happens only twice that I could move. That I could move a result or a theorem from one word to the other. This is one example, this is Ramanujan conjecture, and the other example is the Lustig duality, where this time-bare object plays a parallel role, but other than that, sometimes like tempered is a failure, for example. Moving the temp, like we were discussing, moving the tempered definition from one word to the other is still failing. So I'm not familiar with what work you're referring to. I'm sure it has the same roots. I'm not sure there is any precise.
Yeah, Lustig's series of papers on what he calls the generalized Springer correspondence. We can discuss later.
Yeah, sounds good. Nothing pops up to mind.
Yeah, thank you. Thank you.
I just have two really quick questions. In the original Ramanujan conjecture, there's this parameter going to infinity that the boundedness is what's important there. Can you interpret the parameter as living on bungee, a parameter on bungee for some curve, for some bundle?
I mean, I can interpret temperate in terms of R2 parameters, but again, there will be geometric R2 parameters, and that's essentially singular support. So with a lot of imagination, yes, but no numerical.
Is it for an elliptic curve or for P1 or for what curve?
So you can do it for any curve. So
okay.
another way to say what tempered is well, I mean, it's hidden in what I said. So what does it mean quasi-coherent shifts? Those are incoherent shifts with zero singular support, with singular support concentrated on the zero section. But this H minus one of the cotangent bundle is the space of R2 parameters. And so if you believe in Langlands, or if you use the Ratsetake, so a tempered thing is, tempered object is an object with R2 parameter concentrating on the zero section, so with zero R2 parameter. So that's the rough analogy. And it can be made, it's in progress, it can be made more precise in certain contexts. But it's related to recent work of Distler and other people, 5 people.
Okay, thanks.
Beyond that work.
So I don't see any other hands raised. So if are there any other questions? Okay. In that case, let's thank Dario again.
Okay.